These are the notes for Module J, Unit 3, Lesson 1, and a little bit of Lesson 2. The topic is the electromagnetic spectrum. The essential question says, what is the relationship between various EM waves? And I broke it down into specific learning targets again. The first is, I can distinguish between the parts of the electromagnetic spectrum using wavelength and give examples of them. Second is, I can explain characteristics of an electromagnetic wave. So that means recognizing that it's a wave that can travel without a medium, and that they are transverse waves. And then lastly, we're going to skip part of this learning target. So I can explain the difference between, we're going to skip I can explain the difference between and just do I can explain what determines the color of the objects we see. We did not do the lesson preview together in the workbook. So let's jump right to the notes. In class, I had all students watch the digital lesson and complete the notes as they watched because we're talking about something that's really visual, and so the pictures in the digital lesson I think are really helpful and will help you to make some connections. So if you haven't watched it yet, you should watch the digital lesson on Think Central. It's assigned, so you'll find it in the Things to Do tab. The first question is, what type of light causes sunburn? And that's UV or ultraviolet light. And then what type of waves are light waves? They are electromagnetic or EM waves. All electromagnetic waves travel at the speed of light. That's 300 million meters per second, or 3.0 times 10 to the 8th meters per second. When electromagnetic waves travel through a vacuum, through a medium, they slow down. Electromagnetic waves only travel at 300 million meters per second when they're in a vacuum, when they're in empty space. And when they reach Earth's atmosphere, they slow down because they're entering a new medium. And that's true anytime they travel through a new medium. And then radiation, one of our vocab words from this lesson, is defined as energy that travels across distances as electromagnetic waves. Electromagnetic waves travel along electric and magnetic fields at right angles to the fields, and that's how they get their name. This is a picture of what those EM waves look like traveling through those fields. And electric and magnetic fields are all around us all the time. We don't notice them, but that's what those electromagnetic waves are passing through. In your notes, you've got a table where we organized electromagnetic waves by increasing energy and decreasing frequency. So radio waves at the top have the longest wavelength of all the waves we'll talk about here. They're longer than a football field. So the distance from crest to crest is more than 100 yards. And these waves have the lowest energy level. We found them in all sorts of places. They're used by cell phones, TVs. They are used by radio stations. That's how they emit their signals. And different radio stations or cell phones or TV stations emit their signals at different frequencies, and that's how we get the variety that we have. Microwaves are next. There's a big jump here. We went from waves that are measured at more than a football field long to waves that are measured in centimeters. So they're much higher energy than radio waves. And microwaves are used for things like the weather forecast. Infrared wavelengths of light have wavelengths from the size of a pinhead, so the point of a pin, to a cell in your body. That means they're microscopic. You can't see them with your eyes. And infrared radiation is found in things like remote control. When you go to change the channel on the TV or change the volume, the military has infrared glasses that they can use to see things at night. They detect heat. Some animals can see infrared wavelengths or sense them. Snakes, some types of snakes can sense that heat, that infrared radiation. Visible light is the only part of the electromagnetic spectrum that humans can see. Each color of the rainbow has a different wavelength, starting with red, the longest wavelength, and working our way to violet, the shortest wavelength. And so an example is a rainbow, the visible spectrum. It's the light that comes from the sun and from overhead lights in the classroom. Ultraviolet light has wavelengths from 400 down to 10 nanometers. So that's smaller even than things that are microscopic. And this is what causes sunburn. Their UV light can be broken into UVA and UVB rays. And a little bit of exposure to these is good because it helps your body to produce vitamin D, which is a vitamin that helps make your bones strong. But much more than that, much more than about 10 minutes without sunscreen can cause sunburn. And repeated exposure, repeated sunburns can lead to skin cancer. Some animals, like bees, can see ultraviolet light. We'll look at some pictures here in a minute. X-rays range in wavelength from 0.01 up to 10 nanometers, so very small, very high energy. And we've all had experience with X-rays. They're used to get images of bones and teeth. The way they work is that those rays pass through the soft tissue on your body, the muscles and tendons and ligaments. They're reflected by the harder, more dense bones, and so that's why those show up bright white in the X-rays. And then gamma rays are the shortest wavelength of the things that we're looking at here on the electromagnetic spectrum, so they're the highest energy. That makes them really harmful. They can be used there's a new medical device called a gamma knife. So it's used like a laser beam to target and kill a very small specific area of the body and kill cancer cells without damaging the healthy tissue around them. They're also found in nuclear reactions, which gives you an idea of how harmful they are. Here are some images to illustrate some of the things we talked about. This is an infrared image of a cat. So the brighter yellow and white here, those are hotter parts of the cat's body. And then the blue and purple in the background, those are colder parts of the picture. And then here is a picture that shows, this is the way we would see a plant and a flower. And this is the way a bee would see it with that ultraviolet light. And then there's a picture in the digital lesson, and it shows that the pollen kind of glows like a bright yellow to really attract the bee with that ultraviolet light. The visible spectrum of light is next in your notes. It starts with red wavelengths of light, which are the longest wavelengths. And then we go in order of decreasing wavelength and increasing energy. So as we work our way across from red to violet, the waves are shorter and the higher energy, higher frequency. So it's red, orange, yellow, green, blue, indigo, and violet. You've probably heard the acronym ROY-G-BIV. And then when you look at the electromagnetic spectrum here in its entirety, you'll see just how small a portion of it humans see as visible light. Everything to the right here, those are longer wavelengths that we cannot detect with our eyes, and everything to the left, those are shorter wavelengths that we can't detect with our eyes. But there are organisms that can see many more parts of the spectrum than we can, such as the mantis shrimp, and apparently pigeons can see more spectrums than we can. Then and then one last thing on this slide, the last question in your notes is about sunlight. No, sunlight is not always harmful to us. Obviously, we need it to grow plants, helps our bodies produce vitamin D, but with so many things in life, a little bit is good, too much, not good. In Unit 3, Lesson 2, we skipped over much of the notes today and focused just on this section here. So the connection between what we're learning about electromagnetic waves and what we see is that we see only the colors that are reflected. So an object that is white is reflecting all wavelengths of the visible spectrum. An object that is black absorbs all of the colors, all of the wavelengths of light. And because of that, it's absorbing a lot more energy. That's why if you have a black home jersey for a sport and a white away jersey, you're going to be hotter the days that you're wearing the black jersey. If we see things that are a mixture of colors, then they're reflecting more than one color. So something that's turquoise is reflecting some blue and some green wavelengths of light. But if we look at just the purest colors, a shirt that's blue is reflecting only the blue wavelengths of light, and it's absorbing all others. So our eyes only detect the blue wavelengths, or a shirt that's red reflects only the red wavelengths of light and absorbs all others, and that's why we see that shirt as red. And then light travels at a speed that's determined by the medium that it's passing through. We talked about that at the very beginning of the lesson. So in those Unit 3 Lesson 2 notes, these things right here are all that you need to record and all that you'll be responsible for on the test. You don't need to worry about filling the rest out. Those are the notes for Mod J Unit 3 Lesson 1.